If you want to build the future, you might have to leave the ground behind. In the centuries to come, humanity might be known not for how we conquered the land, sea, or air, but how we learned to build among the stars. For most of history, the Earth has been the only factory we knew, bound by gravity and atmosphere, shaped by the limitations of its surface. But orbit offers something new, a realm of endless possibilities, where gravity, pressure, and even raw materials can be tailored to our needs. Today, we're already taking the first steps into that future, experimenting with manufacturing in the weightlessness of orbit. And while these early projects are small, delicate fibers, perfect crystals, tiny tissues, they are the seeds of something far greater. In this episode, we'll explore how zero gravity and space-based foundries could transform our world and eventually build entirely new ones. We'll journey from the first experiments aboard the ISS and commercial satellite factories to the vast orbital industries that could one day turn entire asteroids into starships and weave Dyson swarms around suns. It all starts with a single thread pulled in zero-G gravity, but it might end with us manufacturing the very stars themselves. Why manufacture in space? For thousands of years, human industry has been shaped and shackled by the conditions of Earth. Gravity pulls, air resists, heat rises, and impurities creep into every process. Even with all our advancements, we still wrestle with the basic forces of nature to refine materials, build machines, and grow delicate biological systems. But space offers something Earth never could: freedom from those old constraints. In orbit, the near weightlessness of microgravity lets us create structures and substances that would collapse, warp, or fall apart under their own weight on Earth. Imagine you're on Earth mixing two substances together, whether it's paint, jello, or any of a million other things. Sometimes they react to form a new molecule, but often you're just dissolving one into the other, like sugar into water. In a simple case like sugar water, the amount of sugar is nearly the same everywhere in the glass. But for many mixtures, especially when you need a very precise and uniform concentration, gravity can cause heavier components to sink and lighter ones to rise, creating unwanted separation over time. In microgravity, however, that settling doesn't happen. Without gravity pulling substances apart, diffusion and molecular motion dominate, allowing mixtures to stay far more uniform and stable, a huge advantage for precision chemistry, material science, and even growing perfect crystals. Crystals can grow larger and purer without gravity dragging their structures down. Molten materials can mix more uniformly without heavier elements sinking to the bottom. Delicate biological tissues like cartilage or even entire organs can form without needing scaffolding to hold them together. And it's not just the lack of gravity. The vacuum of space itself is an enormous asset, a perfect, natural environment for processes that require ultra-pure conditions. No air means no oxidation, no contamination by airborne particles, and no need for heavy, energy-intensive clean rooms we rely on down here. Whatever air mixture and pressure we desire, we can create, and while your own mix will slowly leak into the vacuum of space, nothing leaks back in. Anything that leaks out, like dangerous bacteria and viruses in a lab, are not going to live. No air or liquid, and lots of harsh radiation to sterilize things. Though I will note as a caveat that we have found some very impressive microorganisms that seem able to stay barely alive in those conditions, and you might have organisms living on the leaking crack of a space station, especially cracks shielded from direct light. Regardless, they won't be thriving there, but research might, without needing to worry as much about contamination as down on Earth. Then there's the energy question. In space, sunlight is constant and strong, other than in low orbit, where you pass into Earth's shadow a lot, and even there, your dark phases are less than an hour followed by full sun again, making operating on batteries a lot easier than on Earth. In higher orbits, solar panels can collect power around the clock, without worrying about cloudy skies or nighttime. For the energy-hungry process of industry, that's a game changer. Of course, none of this comes without a cost. Launching anything into space has traditionally been extraordinarily expensive, and even today, getting a payload into orbit can cost thousands of dollars per kilogram. That's like trying to build a factory where every brick costs as much as a gold bar. But that cost is coming down. Even ignoring game-changing options like space elevators, which could slash launch costs by orders of magnitude, we're already seeing reusable rockets like SpaceX's Falcon, Starship, and Blue Origin's New Glenn offer a path to space that might be merely hundreds of dollars a kilogram, and that's more than enough to make it viable to grow various high-value, low-mass objects like semiconductors and computer chips. We're starting to see a world where sending material to space is no longer reserved for billionaires and national governments. One day soon, launching a payload might be more like shipping a cargo container across the ocean, a major cost, but manageable for the right high-value products. And that's the key. For space manufacturing to be viable, at least at first, it must focus on things that are so valuable that they outweigh the enormous cost of doing business off-world. Materials that are more perfect, more powerful, or more profitable than anything we can make at the bottom of Earth's gravity well. The physics of space doesn't change how we get around, it changes how we build, how we grow, and even what's possible to imagine. As we'll see next, the first seeds of this new industrial revolution are already being planted in orbit right now. Near-term zero-G manufacturing efforts. While visions of massive orbital factories and asteroid smelters are still decades away, the first steps towards zero-gravity manufacturing are already underway, and they're happening closer to home than you might think. The International Space Station, or ISS, has been humanity's main platform for experimenting with manufacturing in space, and though the ISS is often thought of as a science lab or an outpost for astronauts, it has quietly become a small but critical testbed for the zero-gravity industry. Indeed, when folks ask me why we don't have a space station with a rotating section simulating gravity, I always feel it important to note that we have lots of gravity down here on Earth, and at the moment, just one very expensive and tiny place in which to conduct any zero-G research and development. What we have done thus far, even with those limitations, shows a lot of potential. One of the most promising efforts has been the production of Z-band optical fibers, a special type of fiber made from a fluoride glass containing elements like zirconium, barium, lanthanum, aluminum, and sodium. On Earth, where Z-band fibers are drawn, gravity tends to cause tiny imperfections, crystals, and defects that limit their performance. In microgravity, those imperfections are dramatically reduced, resulting in fibers that could theoretically transmit data many times faster and farther than traditional silica fibers, with far less signal loss. Given how vital high-speed communications are for everything from finance to medicine to military operations, a better fiber could be a very big deal indeed. We might expect the same from options like carbon nanotubes, graphene, and other 2D materials where performance relies on very few imperfections in the material. Ironically, such super materials are one of our best pathways to being able to reach space cheaply, though this is a catch-22. As we weave our future, we are likely to see a lot of incremental improvements to getting there cheaper that will make manufacturing there even cheaper and unlock yet more ways to get to space cheaper in the process. Beyond fibers, microgravity has proven to be a powerful environment for biological work as well. Researchers aboard the ISS have experimented with growing larger and purer protein crystals, which can help in drug design by providing clearer structures for pharmaceutical development. They've also explored bioprinting tissues and even primitive organ structures, growing delicate, scaffold-free tissues that simply are not possible to create under Earth's gravity without artificial supports. The hope is that in the near future, we might manufacture everything from artificial cartilage to transplantable organs in orbit, a life-saving application with an enormous economic upside. And as an example of cost, while it doubtless takes more than the mass of a heart up in space to manufacture them, you need labs and people or robots running them too, a new heart or other organ is definitely worth thousands of dollars a kilogram on the current market. That represents a potent motivation for government R&D funding, given that such expenditures, assuming they are reasonably successful, would likely be popular with the taxpayers and voters. Meanwhile, the private sector has already started moving in. Made in Space, one of the early pioneers, developed the first 3D printer designed to operate entirely in microgravity, producing basic tools and parts aboard the ISS itself. Their long-term vision, embodying the Archinaut program, is to build entire satellites, trusses, and solar arrays directly in space, bypassing the need for expensive forwarding mechanisms and risky deployments. It is easy to forget that a lot of a given satellite's engineering is designed to be able to handle both Earth's gravity, since we have to build it here, and the insane engineering needed to survive launch. If a satellite can be built in orbit instead of surviving the violent stresses of launch, it can be lighter, larger, and longer lasting. Another company, Orbital Space Industries, is taking a different approach, building small, autonomous manufacturing satellites designed to produce high-value goods in orbit and then safely return them to Earth. Their early focus is on pharmaceuticals, advanced materials, and potentially exotic semiconductors, products where even tiny improvements in quality could be worth millions, and where the value-to-mass ratio is already very high. And they are not alone. Most startups and government agencies are beginning to eye zero-G manufacturing for niche, ultra-high-value products. Advanced semiconductors for faster and more efficient electronics, exotic alloys and supermaterials for aerospace and defense, ultra-pure biological compounds for research and medicine, specialized foams and metamaterials that require slow, uniform formation in microgravity. The key for now is finding products that are high value per kilogram and low risk per mission, items so valuable and so uniquely suited to microgravity production that they justify the high cost of space operations. Of course, these early efforts are not without challenges. Returning products safely to Earth remains a major hurdle. Capsules must survive the fiery plunge through the atmosphere, keeping their delicate cargo intact. Space stations and satellites must be built and maintained without easy access to spare parts or repair crews, and all of it has to be made cost-effective enough to compete with Earth-based alternatives. Still, the groundwork is being laid. With every fiber drawn, every protein crystal grown, and every bioprinted tissue formed in orbit, we will gain the knowledge and experience needed to make the next steps, building bigger, more ambitious, and more self-sufficient foundries in space. And as we'll see next, those future orbital factories may change not just how we manufacture goods, but where and what we choose to build. Midterm, orbital foundries and industrial expansion. As launch costs continue to fall and orbital infrastructure matures, zero-gravity manufacturing will move beyond experimental project and niche products. In the coming decades, we'll see the rise of true orbital foundries, dedicated facilities in space, designed from the ground up for industrial production on a scale never seen off Earth. Not quite the megastructures we often envision on this show, even the more modest ones like O'Neill Cylinder or Stanford Torus, but setting the stage for them by getting both the industry in place robust enough to build them and the population workforce in space need to inhabit them and justify building them. That's a ways off, and even the midterm of thousands of folks working and living in space is decades away. The first wave will likely be small, modular, and largely robotic. Think of compact industrial parks orbiting Earth, clusters of autonomous factories linked together by communication satellites and robotic maintenance drones, powered by vast fields of solar panels. Possibly with some crew maintaining the facilities and experiments, maybe enough to justify a von Braun wheel, especially as extra space might be rented to other R&D or even as a space hotel. These factories might focus on specific high-value tasks, growing perfect crystals, assembling advanced electronics, manufacturing exotic alloys, and bioprinting organs or tissues that cannot reliably be made in terrestrial labs. And crucially, these facilities might not have to launch all their raw materials from Earth. ISRU, in-situ resource utilization, is a familiar concept to regular viewers and space enthusiasts alike, but it cannot be emphasized enough how important being able to get bulk raw materials to orbital foundries would be. Some scenarios like orbital rings and space elevators might actually let us get materials up from Earth very cheaply, but otherwise, a big turning point will be the ability to source inputs directly from space itself. Asteroids, near-Earth asteroids in particular, of which are tens of thousands, offer a tantalizing supply of metals like iron, nickel, platinum, and cobalt, not to mention water ice, which can be turned directly into drinking water, oxygen, or rocket fuel. As does the Moon. Though drier and less metal-rich, it could supply huge quantities of regolith and basic building materials at relatively low cost compared to lifting them from Earth's deep gravity well. In the midterm, expect a gradual shift from purely Earth-launched inputs to a hybrid model, where bulk materials come from asteroids and moons, and specialized components or personnel still arrive from Earth. Construction methods will also evolve rapidly. Instead of launching large, fragile structures folded into cramped rocket fairings, orbital foundries will use additive manufacturing, essentially giant 3D printers, to build directly in space, though additive manufacturing does cover a lot more options than simple 3D printing. We'll print everything from communications arrays and solar panels to modular habitat frames to the skeletons of deep space vessels. In zero-gravity, structures can be far larger and lighter than anything built on the ground, because they don't need to survive the crushing force of a launch or the constant tug of gravity. What products will dominate this phase? Presumably the same kind of goods that benefit the most from microgravity and vacuum manufacturing. Superalloys with perfect molecular structures for turbine blades, spacecraft, and advanced engines. Ultra-pure semiconductors for quantum computers and ultra-fast communications. Exotic foams and metamaterials that require slow, uniform curing without gravitational distortion. Biological tissues and organs, essential for future space colonists as well as medical breakthroughs on Earth. But we will also see a lot of ramping up for bulk production, metal plating for keeping air in and radiation out, fuel and propellant production for moving around orbit or to other worlds, and possibly some actual food production at this point. Your price for a day's worth of food and water, even with air recycling, is likely about the same as your price per kilogram to get to orbit, and it is likely to come down to hundreds of dollars a kilogram by this stage. But eventually, your price point for maintaining and staffing some sort of orbital farm is likely to be less than flying food up, especially for produce. See our space farming episode for more discussion of that topic. And while space station plating, fuel, and food are likely to be our first entrance into manufacturing in space for space, as orbital manufacturing scales up, we will likely see a virtuous cycle emerge. Factories build more factories, space habitats support more workers, mining missions supply more materials, additional items become more viable to produce in space, while at the same time bringing things up from Earth also gets cheaper, and the orbital economy gains funds to make purchases with. With each new step, the space industry becomes more self-sustaining, less dependent on Earth, and more capable of fueling its own growth. Of course, none of this will happen overnight. There will be setbacks, accidents, and economic bottlenecks, and we must be mindful that often things that look like they'd soon be viable to make in space will turn out to be more expensive than first planned. It will be slow. Building anything in space is a challenge, let alone creating entire industrial ecosystems. But history shows that wherever humans find a profitable frontier, they find a way to tame it. And orbit is shaping up to be one of the richest frontiers we've ever seen. If nothing else, always remember that 99.9997% of everything in this solar system is off Earth, and this solar system is but one star among billions and billions in this galaxy, and developing orbital space is the gateway to that galaxy. Eventually, it is the place where those orbital foundries build the spaceships that will take us to strange new worlds. By the end of this phase, we may no longer think of orbit as a place you merely visit or pass through. It will be a place where things are built, refined, and created, an extension of civilization itself, hanging above the Earth like a glittering belt of industry. And speaking of the galaxy, once we master building an orbit, it's only natural to ask, why stop there? In the next section, we'll look at how space manufacturing could scale beyond orbit, reshaping not just our skies, but the solar system itself. Before we jump into the long-term scale, I want to take a quick moment to thank our long-term supporters over on Patreon, who made this and many other episodes possible. We talk a lot about futures worth building, and if you'd like to help build them here, consider joining our Patreon. Just use the QR code or the link in the episode description. It turns ideas into episodes. Long-term, true orbital foundries and gigascale production. Guessing timelines for space development is always tricky. Folks tend to be overly optimistic about how soon we'll get a true foothold, and then overly conservative about how fast things will avalanche once that foothold is established. But if I had to guess, I'd say that sometime in the 22nd century, orbital industry will reach a tipping point, a moment when space is no longer just a place we work in, but the foundation of an entirely new civilization. Companies won't just be paying outrageous prices to house the minimum number of workers they absolutely need on site. You'll start seeing investors seriously eyeing the prospect of selling real estate to people who want to live in space, because it offers something Earth no longer does: new space. If you're thinking that time might never come because robots can do all the work better, that may be true to a degree, but it misses an important point. If automation gets that good, it actually becomes easier and cheaper to build giant housing developments in space, because the overall economy will have far more production and wealth to throw at such projects. In fact, in a future where AI and robots help us tame space, humans are not replaced, they are empowered. It becomes easier to send people, and people want to go. At this stage, we're not just talking about small factories orbiting Earth. We're envisioning vast orbital stations, colossal structures dedicated entirely to manufacturing, construction, and heavy industry. Some of these may be kilometers across, supporting tens of thousands of autonomous machines and hundreds or even thousands of human workers living in rotating habitats nearby to maintain long-term health in artificial gravity. And depending on how Earth's population growth sits, which is also very hard to predict, it may be stable or declining or growing fast, and at the latter a big source of revenue in space might be industries subsidized by countries wanting them to build orbital habitats to send people to. Either way, once you develop the space industry to any modest level, energy will no longer be a major limitation. By this point, space-based solar power stations could be common, with huge orbital arrays beaming gigawatts of clean energy either back to Earth or directly to orbital facilities. Energy-hungry processes like smelting metals, cracking chemical bonds, or assembling giant structures will no longer need to ration power. The Sun, after all, is a 400 trillion watt power plant, and space gives us direct access to its output. With abundant power, raw materials from asteroids and the Moon, and growing orbital infrastructure, humanity will be able to attempt projects we can barely dream of today. Instead of sending fragile payloads up from Earth, we will build in space for space. What we build now will be large in quantity and variety, but some big-ticket items would likely include the following: solar-powered satellites the size of cities, assembled in orbit and beaming power to the ground; interplanetary ships, kilometers long, built without concern for launch stresses or gravity; space habitats, spun for gravity, capable of housing thousands or even millions of people; true cylinders, constructed like giant ships in a sea of stars; massive telescopes, bigger than anything that could ever survive a rocket launch, floating silently in the vacuum between worlds. We may even begin building structures so large they might qualify as megastructures. These might include rings of infrastructure encircling Earth, growing to full orbital rings; dense clouds of energy collectors and foundries swarming around the Sun, the first steps toward a Dyson swarm; asteroid refineries so vast they gradually hollow out entire minor planets, repurposing them into industrial colonies, habitats, or starships. At this stage, automation and self-replication will be essential. No human workforce could manage the sheer volume of material and activity needed to grow space industry to planetary or solar system scales, at least not without us patiently breeding up our numbers. We could do this manually without a lot of robots if we decide we can't trust them or make them work well, but I don't see that as likely. Instead, autonomous mining bots, construction drones, and 3D printers the size of office buildings expand our reach faster than the human workforce alone ever could. These self-replicating industrial systems will mine asteroids, refine metals, and fabricate structures, expanding not linearly but exponentially. The solar system itself has become an extension of the factory floor. Lunar bases churn out materials and water. Perhaps Mars provides heavier manufacturing and settlement. Venus has a near endless supply of nitrogen and carbon we want. Comets and icy moons provide all the water we want. The asteroid belt supplies an endless river of metals and minerals, and all of it flows back to orbit to feed the colossal foundries and shipyards growing among the stars, while also growing those settlements around these once barren worlds, and providing them the resources to begin making homes and gardens on no longer dead regolith. But for every new settlement around another planet, moon, or asteroid, another will spring up in orbit, if not several. Orbital space will grow far faster than other places, possibly faster than all of them combined, because it is so close to Earth, where everyone's families are, and where everyone's customers are too. At this point, industry is no longer limited by Earth's surface, or even by planetary surfaces at all. It is free, unbound, able to stretch across the void, to scale with the ambition of whatever humanity dares to imagine. But even this, grand as it is, might only be the beginning, because if we can master building in orbit and across the solar system, then in time we might not just build ships and stations, we might learn how to manufacture whole worlds, vast colony arc ships to travel and terraform new worlds, vast cylinder habitats here for humanity to spill into, but even grander construction perhaps. And as we'll explore next, the far future of space industry could see us assembling not just habitats and megastructures, but planets, and perhaps even galaxies themselves. Far future, manufacturing planets, stars, and beyond. As we project further into the future, the scale of human ambition and capability may transcend even the vast orbital foundries and megastructures we've previously discussed. The ultimate expression of space-based manufacturing could involve the construction of entire planets and the manipulation of stars themselves, and it wouldn't be SFIA if we didn't push into the bounds of truly epic constructs in the deeper future. Constructing artificial planets. The idea of building planets from scratch, while still firmly in the realm of science fiction today, could one day become feasible for a civilization that has mastered the energy and resources of its solar system. Such a monumental project would begin with resource acquisition, harvesting vast amounts of materials from asteroids, moons, and even entire planets. These raw materials will then be assembled into planetary structures using advanced robotics and autonomous systems, operating seamlessly across the vacuum of space, as we've detailed in the Megastructure Compendium and series. Once the physical framework of a planet was completed, the next step would be atmosphere and biosphere engineering, introducing the right gases, water, and eventually life forms to create habitable environments. These artificial planets could be tailored for a variety of purposes, designed for habitation, scientific research, recreation, manufacturing hubs, or as launch points for deeper space exploration. Sometimes sheer scale can be deceptive. Manufacturing a shell world may be only an order of magnitude harder and costlier than building the same massive cylinder habitats. It deserves mentioning that if we imagine every adult human currently alive moving 10 tons of material every hour for a 2,000 work hour a year, it would take us 50 million years to move a planet's worth of mass. Given that a planet is good for 100 times that long right now, that is not necessarily a bad investment of time, but understand that even with automation beyond anything we currently have under design and near limitless power, building planets is quite an undertaking. It also uses a lot of material, and surprisingly the best place to harvest for rocky materials and metals turns out to be the sun itself, at least when you need planetary quantities. Starlifting and stellar engineering. Beyond planetary construction lies that even grander concept of stellar engineering, beginning with starlifting, the process of extracting material directly from a star. Several methods have been proposed for this, including the use of powerful magnetic fields to channel plasma away from the star's surface, or laser ablation, employing concentrated energy to heat and eject stellar matter. See our starlifting episode. Starlifting could serve multiple objectives. It would provide raw materials on a scale far beyond what planets and asteroids could offer, supplying resources for megastructures and other massive construction projects. It could also allow civilizations to manage a star's lifespan, either extending it to provide a stable environment for longer periods or altering it for other specialized needs. Dyson swarms and beyond. One of the most iconic megastructures often associated with advanced civilizations is the Dyson swarm, a vast array of satellites orbiting a star to capture its energy output. Constructing such a swarm would represent a major leap forward in energy acquisition, offering near limitless power to sustain civilizations and fuel their ambitions. With the abundant energy provided by a Dyson swarm, even grander undertakings become possible. Structures like Matryoshka brains, layered shells of Dyson spheres designed for vast computational tasks, could be built to house civilizations of staggering scale, or to perform simulations and data processing on an unprecedented level. Stellar engines, machines capable of gradually moving entire stars and their planetary systems, could also be developed, allowing civilizations to steer their solar systems through space if needed. As we contemplate these possibilities, it becomes clear the trajectory of space-based manufacturing leads toward ever greater horizons, from crafting delicate fibers in microgravity to constructing planets, harnessing stars and building immense artificial ecosystems, the potential of human and post-human innovation seems boundless. Each step forward brings us closer to reshaping not just our world, but the very fabric of the cosmos itself. From tiny threads to stellar foundries. We began this journey with a simple idea that in the centuries ahead, humanity might not be remembered for the lands we conquered, but for the worlds we built and the stars we shaped. Today, we are only at the beginning. Our first steps in orbital manufacturing are cautious, experimental, drying delicate fibers, growing crystals, and printing tissues in the weightlessness of space. These are small, fragile threads compared to the towering possibilities ahead, but every great structure begins with small foundations, and every future, no matter how distant or grand, is woven from the efforts of those first daring enough to try. As we move from building satellites and solar panels to assembling entire habitats, to harvesting the material of asteroids and the stars themselves, we are laying the groundwork for a future where creation knows no limits, a future where Earth is no longer the center of human industry, but just one planet among many, one node among billions, in a thriving, star-spanning civilization. It starts with a handful of fiber optic strands, spun in the quiet hum of a space station, but it could end with Dyson swarms, Matryoshka brains, and even the crafty of new stars and worlds, built to suit the dreams of countless generations yet to come. Because when you learn how to build among the stars, there's no limit to what you can create, or where you can go next.